Unit 9, Gases. By the end of this unit, you will be able to determine the amount of gas produced in a reaction, describe the relationships between volume, pressure, number of moles, and temperature for an ideal gas, explain the following laws that pertain to gases: Boyle's law, Charles' law, Avogadro's law, Dalton's law of partial pressures, and the ideal gas law, and describe the postulates of the kinetic molecular theory. Properties of gases. Gases are matter. They have mass. They take up space. They exert pressure. They expand to completely fill their containers. They can be compressed or expanded. They have low densities. And particles spread out or diffuse. The kinetic molecular theory. What is the kinetic molecular theory? The kinetic molecular theory, or KMT, is a set of rules or postulates that explain the behaviors of gases. These postulates describe ideal gases. What are the postulates of the KMT? 1. Gas particles travel in a constant, random, straight-line motion. 2. Because gas particles are so small compared to the space between particles, they are thought to have no volume. 3. Gas particles have perfectly elastic collisions with other particles and their containers. They bounce off of other things, so they do not lose energy when they collide with something. And 4. There are no forces of attraction or repulsion between particles. Gases follow the 4 postulates of the KMT, except for when there is high pressure or low temperature. Why would those 2 circumstances cause a gas not to act ideal? At high pressure, the gas particles are closer together. That means the space between particles is decreased. At high pressure, the volume of the gas particles becomes significant. At low temperature, the particles are moving slower, so that increases the amount of attraction or repulsion between particles. Describing gases. How can we describe gases? There are 4 different ways to describe gases: pressure, volume, number of moles, and temperature. How do we measure gases in the lab? Experimental conditions, such as temperature and pressure, in the lab can affect gases. Scientists use STP or SATP when working with gases to standardize measurements. STP is standard temperature and pressure, 0 degrees Celsius and 1 atmosphere. SATP is standard ambient temperature and pressure, 25 degrees Celsius and 1 atmosphere. What is pressure? Pressure is defined as force over area. Pressure can be measured with a barometer using several different units. You must be able to convert between all of them. A barometer reads 743.2 millimeters of mercury. What is this in atmospheres? So we're going to use dimensional analysis. Remember, our first box is what we were given in the problem. So 743 millimeters of mercury. What we're looking for goes in the top box. So 1 atmosphere. And the units that match what we were given go in the bottom box. So when you calculate that, you have 0.9779 atmosphere. A tire is inflated to 32.2 psi. What is this in kilopascals? So again, we're going to use dimensional analysis. We have 32.2 psi. We need to get to kilopascals. So we're looking at our conversion factors. So 14.1 psi is 101.3 kilopascals. So we're looking for kilopascals, that goes at the top, and the psi, 14.1 psi, goes at the bottom. So we have 231.3 kPa. Okay, in our last example, we have 352 torr. We need to know how many atmospheres. So 352 goes in the first box. We're looking for atmospheres. So 1 atmosphere is equal to 760 torr. So the 760 torr go at the bottom. And we have 0.463 atmospheres. If you need a refresher on dimensional analysis, check back with the moles video. What is volume? Volume is the space a substance takes up. Gases will expand to fill their containers. In an experiment, you collect 52.2 milliliters of CO2. What is this in liters? So we'll use dimensional analysis, 52.2 milliliters. We need to get to liters, so 1 liter equals 1,000 milliliters. So we have 0.0522 liters. Remember, the number of moles is the amount of gas particles. So 1 mole of gas at STP, standard temperature and pressure, is 22.4 liters. It is also the molar mass of the gas. So how many moles are in 4.25 liters of argon gas at STP? So we start with what we're given, 4.25 liters. We're looking for moles. So our 1 mole of gas goes at the top. The 22.4 liters at STP goes at the bottom. So we would have 0.1897 moles of gas. What is temperature? Temperature is a measure of the average kinetic energy of a substance. When working with gases, the temperature is measured in Kelvin. To convert from Celsius to Kelvin, add 273. To convert from Kelvin to Celsius, subtract 273. 0 Kelvin is absolute zero, the theoretical temperature where all molecular movement stops. Describe the motion of a gas particle that is at a temperature of 750 degrees Celsius. Quick check. What is the temperature in Celsius if the temperature is 872 Kelvin? So to find Celsius, we take the temperature in Kelvin and subtract 273. So we have 599 degrees Celsius. What is negative 32 degrees Celsius in Kelvin? So to find Kelvin from Celsius, we're going to add 273. So we have negative 32 plus 273, so 241 Kelvin. And what is 1,154 degrees Celsius in Kelvin? So we add 273, we get 1,427 Kelvin. Ideal and real gases. What does it mean for a gas to be ideal? Ideal gases are theoretical gases that perfectly follow the rules of the kinetic molecular theory. Do all gases follow the rules of the kinetic molecular theory? No. Real gases don't perfectly follow the rules of the KMT. When are real gases most like ideal gases? Real gases act the most ideal at high temperatures and low pressures. So ideal gases, the particles take up no space. In real gases, the particles take up some space. In ideal gases, there is no attraction between the particles. In real gases, there are some forces of attraction between particles. And in ideal gases, particles do not slow down after collisions. In real gases, particles do slow down after collisions. So which of the following would you expect to behave the most like an ideal gas? Why? Remember that gases behave the most ideal at high temperatures and low pressures. So helium at 0.5 atmospheres would be more ideal than helium at 1.9 atmospheres. And oxygen at 1500 degrees Celsius would act more ideal than oxygen at 200 degrees Celsius. The ideal gas law. What is the ideal gas law? The ideal gas law lets us calculate the moles of a gas if you know P, V, and T. This is useful in determining the mass of a gas. So the ideal gas law is PV equals nRT. P is pressure, V is volume, N is the number of moles, R is the gas constant, and T is temperature in Kelvin. What is R? R is the gas constant. The value you use for R will depend on the units that you have for pressure. If pressure is in atmospheres, R is 0.0821. When do you use the ideal gas law? Use the ideal gas law when you are given several variables, but none of them are changing. Quick check. What is the volume of 0.468 moles of gas at STP? We know moles, we know pressure, and we know temperature. Temperature has to be in Kelvin, so 273 Kelvin. And we're looking for volume, so we'll use the ideal gas law. So our first step is going to be to rearrange our equation so we can solve for V. So to find V, we need to divide both sides by P. So V equals nRT divided by P. Now we plug in what we know. So the volume is 10.5 liters. So how many moles are in a 1.45 liter balloon filled with CO2 that has a pressure of 0.98 atmospheres at room temperature? So room temperature is 25 degrees Celsius, so that would be 298 Kelvin. Pressure is 0.98 atm. And volume is 1.45 liters. We'll use the same value that we used in the last problem for our gas constant, since we still have atmospheres. So this time, we're solving for N. So we need to divide both sides by RT. So N equals PV over RT. So now we can plug in what we know. So when we solve for moles, we would get 0.0581 moles. Hey, and the last example. If 0.72 moles of a gas occupy 14.2 liters at 0.82 atmosphere, what is the temperature? So we are looking for temperature. We know moles, we know volume, and we know pressure, so we need to find temperature. So our first step is to rearrange our equation. This time we're looking for T. So we're going to divide both sides by nR. So T is equal to PV over nR. Now we plug everything in. Our volume is 14.2 liters over moles, 0.72 moles, and then times the gas constant. So when you calculate that, you would get 196.9 Kelvin. What about when a gas doesn't behave like an ideal gas? The corrected version of the ideal gas law that takes into account intermolecular forces and the volume that the gas particles take up is the van der Waals equation. A is the average attraction between particles, and B is the volume that the particles occupy. So if you had a gas that had a low temperature or a high pressure, you would have to use the van der Waals equation. Gas laws. What are the gas laws? The gas laws are the mathematical functions that describe the relationships between pressure, volume, temperature, and number of moles. Boyle's law: pressure and volume are inversely related at constant temperature. In other words, when temperature stays the same, if volume is increased, pressure is decreased. Charles' law: the volume of a gas is directly proportional to the temperature at a constant pressure. If the temperature is increased, volume also increases. Gay-Lussac's law: pressure and temperature are directly related when volume is held constant. And Avogadro's law: volume is directly proportional to the number of moles of a gas. Quick check. Which law would explain the following scenarios? Your bike tire appears low on a very chilly morning. So the law that compares volume and temperature is Charles' law. A balloon was placed in the freezer and taken out and placed on a counter. As the balloon sits on the table, it increases in size. So again, this one we are looking at temperature and volume. So Charles' law. When you breathe in, your diaphragm is pulled down, increasing the volume of your lungs. So this one, you are looking at pressure and volume. So that would be Boyle's law. The combined gas law. What is the combined gas law? The combined gas law is a combination of the other four gas laws. You can use the combined gas law to solve problems by crossing out the constants. This will give you the equation you need. The combined gas law formula is P1V1 over T1N1 equals P2V2 over T2N2. How do you use the combined gas law? To use the combined gas law, first identify the variables, things that change, and the constants, things that stay the same, and cross out the constants in the equation. Then plug in the variables and solve. Example 1. A sample of gas has a volume of 1.52 liters when the pressure is 1.25 atmospheres. What is the volume at 0.891 atmospheres if the temperature is constant? So for this one, the temperature and number of moles are constant, so we can cross this out. So the formula that we're using is P1V1 equals P2V2. P1 is 1.25 atmospheres. B1 is 1.52 liters. P2 is 0.891 atmospheres. And V2 is what we're looking for. So we can use any unit for pressure as long as they're both the same. So now we plug in what we know. So 1.25 atmospheres times 1.52 liters equals 0.891 atmospheres, and V2, which is what we're solving for. So we're going to divide by pressure on each side so that we can get V2 by itself. So V2, when you solve, equals 2.13 liters. Example 2. A balloon at room temperature has a volume of 8.60 liters. What is the volume of the balloon if the temperature is increased to 87 degrees Celsius? So the pressure stayed the same. and number of moles stayed the same. So our formula, V1 over T1 is equal to V2 over T2. So T1 was room temperature, which is 25 degrees Celsius. We have to have it in Kelvin, so we're going to add 273, so 298 Kelvin. T2 is 87 degrees Celsius. When we add 273 to that, we have 360 Kelvin. And V1 was 8.60 liters. And we're looking for V2. So now we put everything in the equation. And solve for V2. So the final volume is 10.4 liters. Example 4. A scuba tank has a volume of 8 liters. The gas inside it has a pressure of 23,200 kilopascals. What volume would this gas occupy at standard pressure? So the number of moles don't change, and the temperature doesn't change. So the formula that we're going to use is P1 V1 equals P2 V2. So we know V1, it's 8 liters, and the pressure is 23,200 kilopascals. P2 is at standard pressure, 1 atmosphere, or 101.3 kilopascals. So now we plug in what we know. When we solve for V2, we get 1,832 liters. Dalton's law of partial pressure. What is Dalton's law of partial pressures? Dalton's law of partial pressure states that the total pressure of a mixture of gases is equal to the sum of the pressures of all of the individual gases. So P total is equal to the pressure of gas 1 plus the pressure of gas 2, and so on. You can use any unit of pressure when using this gas law, but you have to be consistent. Quick check. The air around you has a pressure of approximately 1 atmosphere. If the pressure of oxygen is 0.22 atmospheres, and the other gases are about 0.01 atmosphere, what is the pressure of nitrogen? So P total is equal to the pressure of oxygen plus the pressure of other gases plus the pressure of nitrogen. So P total is 1 atmosphere. Oxygen is 0.22 atmospheres. Other gases are 0.01 atmosphere. And the pressure of nitrogen is what we're looking for. So to find just nitrogen, we're going to subtract the pressure of oxygen and the pressure of other gases from the total pressure. So the pressure of nitrogen is 0.77 atmospheres. Effusion and diffusion. What is effusion? Effusion is the movement of gases out of a small opening due to the random movement of particles. What is diffusion? Diffusion is the movement of particles from areas of high concentration to low concentration. How can you determine the rate a gas moves? You can determine the rate that a gas moves by using Graham's law. The rate of diffusion is inversely proportional to the molar mass of the gas. What does that mean? This means smaller, lighter gases can diffuse or effuse more quickly than larger, heavier gases. Quick check. Draw effusion and diffusion. So effusion would be gases moving through a tiny opening based on random movement. Diffusion is molecules spreading out. So going from high concentration to low concentration. And finally, stoichiometry with gases. So now you'll be calculating how many liters of gas are needed in a reaction, or how many liters can be produced. So remember, how big is a mole of gas? 1 mole of any gas at STP is 22.4 liters. How many liters of hydrogen gas at STP are produced if 9.35 grams of magnesium metal is reacted with HCl? So remember from Stoic, our first step is to write our balanced equation. So we have magnesium reacting with HCl, and it produces magnesium chloride and hydrogen gas. So we need a 2 in front of the hydrochloric acid in order to balance our equation. So like we did before, we start with what we're given. So we have 9.35 grams of magnesium. Our first step is always to get to moles. So we're going to divide by the molar mass of magnesium, 24.31 grams in 1 mole. Remember that whenever you use molar mass, you are always comparing it to 1 mole. Then we use our balance numbers. So we're looking at magnesium to hydrogen. So 1 mole of hydrogen compares to 1 mole of magnesium. And now we need to get to liters. So this is the new step. Since this gas is at STP, we can use 22.4 liters per mole. So 1 mole of hydrogen is 22.4 liters of hydrogen. So remember that we multiply everything that's at the top and then divide by each thing that's at the bottom. So when you solve, you get 8.62 liters of hydrogen. What if you have a gas that isn't at STP? If a gas isn't at STP, you must use PV equals nRT as the bridge between moles and volume. So example 2, how many liters of hydrogen gas are produced if 1.5 grams of magnesium metal is reacted with hydrochloric acid at 1 atmosphere and 20 degrees Celsius? So this time we need to find out how many moles of hydrogen can be produced. So we start the same way. We have grams of magnesium. Our first step is always going to be to get to moles of magnesium. So 1 mole over the molar mass. Now we use our mole ratio. So for every 1 mole of hydrogen that is produced, 1 mole of magnesium is used. So this gives us how many moles of hydrogen were produced in the reaction. So we get 0.0617 moles of H2. Now we need to know how many liters. So now you use the ideal gas law, PV equals nRT. We're solving for volume, so volume equals nRT over P. Now we plug in what we know. So we had 0.0617 moles times our gas constant times temperature, which was 20 degrees C. So we're going to add 273 and get 293 Kelvin divided by pressure, which was 1 atmosphere. So the volume that we could produce is 1.48 liters of hydrogen. Example 3. What volume of oxygen at 350 Kelvin and 1.2 atmosphere should be produced when 342 grams of potassium chlorate is decomposed? So we start with what we're given, 342 grams. We need to know the molar mass of potassium chlorate. So 1 mole is equal to 122.55 grams. To review how to calculate molar mass, check out the moles video. So we're going to divide by our molar mass, always compared to 1 mole. Now we use our mole ratio to get to oxygen. So for every 2 moles of KClO3, we make 3 moles of O2. So this will give us moles of oxygen. So we have 4.186 moles of O2 produced. Now we need to know how many liters. So we'll use PV equals nRT. We're solving for V, so we have nRT over P. Now we plug in what we know. So moles was 4.186 times R times our temperature, which was 350 Kelvin, and then divided by pressure, 1.20 atmospheres. So when you solve for volume, you get 100 liters of O2.